So the second thing I want you to see is, how about our fourth order scheme? Okay, our fourth order scheme has to start with a second order scheme with a 1, 2. How many points do we need? We need 4 points to start, right? So yeah, so 1 to 4. And so here, which delta t should we start with? We have already 0. We already have 0, delta t, 2 delta t, 3 delta t. Yeah, 3 delta t is what we need to start, right? Okay. Let's go back to 1. Okay. For th. Okay. So here now, what is the scheme? Oh, I didn't write it down. I should. Okay. So let's write down the scheme. So this is the most recent entry, right? And let's actually rewrite it as if du dt at t minus delta t, right? Because we are thinking the most up-to-date value is ut, so we want to write it in such a way. So 12 delta t and minus ut plus delta t. So that's the plus 2 delta t, right? From minus delta t is actually plus delta t. So plus 8 u of t minus 8 u of t minus 2 delta t, right? And then plus u of t minus 3 delta t. So rearrange the terms. This is the only term that should be on the left hand side. So u of t plus delta t should be equal to I have to actually reverse the signs of everything. So this term first, 8 times ut, and the next let me do this because this is t minus delta t. So I have to say it's what, minus 12 delta t, right, times du dt, which is minus u at t minus delta t, right? This is when I'm using the differential equation. Whenever I see a derivative term, I use the differential equation to get rid of it. All right, okay. And the next term is this. So I have minus 8 times u of t minus 2 delta t and plus 1 of u minus 3 delta t. Right? Any bug I have here? Can you double check this? Oh, actually get a equation to check. That's right. That's right. That's right. Okay, thank you. I think we derived the same thing. So let's implement it. So the implementation is, I have 8 times u fourth order at end, right? So that's the first term. I minus 12 times delta t times u of fourth at end minus 1, right? Dot dot dot. In MATLAB, I need to do dot 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 before I change the line. Minus 8. Well, minus 8 times u fourth and minus 2. Does everybody follow me on this? Okay. And what? Plus 1, right? U of fourth order and minus 3. Okay, any bug do I have? Pardon?
Oh, you're saying, yeah, the second.
Yeah, okay. So that's it, right? So let's don't plot it as black, plot it as red, and run it. What?
10 to the 85.
10 to the 85.
That range is fast.
Sad.
It's gone poorly.
So 10 to the 85.
But unfortunately.
That's unfortunate. That's supposed to be our most accurate scheme, right? So let's refine it to see. Let's give it one more 0. Okay. Huh? Let's give it one more 0.
Nope. Now it just goes away faster.
That has me.
Just goes away faster, right?
Hasn't helped.
I would say there's a typo.
There is a typo.
Yeah.
Okay. So
It's either that or a math error.
So remember, there is actually I just said that the first order scheme is called forward order, right? The second order scheme is called midpoint rule. The fourth order scheme doesn't have a name.
It's bad.
Why doesn't it have a name? Because it's something I invented today. Nobody uses that. And now you've seen why nobody uses that. Because it gets you 10 to the 307. I mean, by the way, the reason is 307 is because this line stopped over here. Beyond that, that's the maximum number that can be represented as a floating point, double precision floating point in a computer.
Isn't it supposed to be the higher order the better?
Yeah, isn't it supposed to be the higher order the better?
It's also more sensitive.
Yeah, increased sensitivity.
So what's going on? I have 5 minutes to explain what's going on. So this lecture we encounter actually two types of instability. Okay. The forward order is actually remarkably stable for this problem. So forward order is actually, out of these three schemes, forward order is actually the best for this particular problem. Midpoint rule is very good for short time integration because it actually converges, right? The finer you make it, if you fix the length of the time integration, the smaller delta t you use, the more accurate the solution is. But it's ultimately unstable. So no matter how small a delta t, if you run it for long enough, the oscillation is going to keep growing. Smaller delta t just means the oscillation takes longer to grow. Okay, so that's one type of instability called eigenvalue instability. We'll analyze next lecture on why that happens. The second instability is the instability that happens on the fourth order scheme. It's fourth order, but it encounters a more devastating way of instability. That's called a zero instability. So the reason it's called a zero instability is that it is not even able to integrate, it is not even able to integrate du dt equal to 0. So if you use the fourth order equation to integrate du dt equal to 0, you get an unstable scheme. I mean, it'll blow up the same way. As long as you don't start with everything being 0, if you try to integrate even this equation, you get the same thing. So the eigenvalue instability that happens for the midpoint rule is a milder instability that, so first of all, it only happens to some equations. It doesn't happen to all equations, right? So different schemes would encounter eigenvalue instability for different ODEs. The scheme itself is still good, and it won't have eigenvalue instability for the type of equations it is built for, right? And we'll study in the next lecture, like how do you figure out what problem is going to encounter eigenvalue instability for what kind of schemes. But the zero instability just means the scheme is unusable, period. All right. So there is not even a name for the very accurate fourth order scheme. That just means the scheme is not usable, period. And we'll also analyze in our next lecture, how do you figure out if your scheme is usable at all or not by doing zero stability analysis. All right. So getting back to our how to solve any ODEs. So what are some good derivative schemes? Now you know all the tricks to derive good derivative schemes. And you also know how to turn a derivative scheme into an ODE solver, right? Just to figure out the latest time point and treat that as an unknown, and all the others are known, including the derivative, because you have an ODE. You can always plug the ODE into the derivative. Third question, do good derivative schemes always make good ODE solvers? No. right? That's the primary thing we will have to figure out in the ODE part of this lecture is, why is, for example, MATLABs have multiple ODE solvers, and each solver is actually pretty complicated. And there is a good reason for that. So we'll study what kind of derivative schemes are good as ODE solvers. And no derivative scheme is a good ODE solver for all equations. And we need to figure out what solver is good for what equations.